Good afternoon. My name is Timothy Sliwinski. I'm with the Cooperative Institute for Research in the Atmosphere. We support NOAA's Global Systems Laboratory in Boulder, Colorado. And so we're working with a lot of different operational weather forecasting codes consistently on a daily basis to try to continuously improve our weather forecasting abilities for the nation. And so we have a lot of motivation for looking at Kokkos. And so this actually kind of started about 2 years ago. If any of you that were there for the 2023 Kokkos user group, I kind of gave a introductory presentation on this before we started, and so this is kind of a follow-up to that. But so overall, we're trying to expand NOAA's ability to be ready to use GPUs and GPUs from all vendors. We don't have any GPUs in our operational supercomputers right now for weather forecasting, but we are actively getting those into operations, especially as things like AI weather forecasting become more and more on the upswing. And so we have to be able to use these GPUs, and we want to maintain high levels of performance and utilization on these, and not just from one vendor, but from all of them, so that we're not locked into vendor lock. We want to reduce the need to develop and maintain multiple implementations of the same code, because we've kind of ad hoc done different pieces and parts in different things like CUDA, OpenACC, OpenCL, and so forth. We kind of want to stop doing that because it's so hard to maintain. And then avoid creating winners and losers when we're doing all these different GPUs. And then we just essentially want to be able to encourage collaboration amongst our partners with different resource availability, because we make a lot of code that gets used by the community, that we share with other partners outside, but we don't necessarily all have the same resources available to us, and so having one code that everybody can just kind of put on their machine and use would be the best way to do this. So why Kokkos? Limited performance portability support for Fortran exists across the CPU and GPU line. I don't know why it's blinking on us so much, but hopefully it'll stop. And so we've tried things like OpenMP, Target, OpenACC. We've done a lot of OpenACC, especially with this particular programming code that I'm going to show later. And we did OpenACC originally because we thought it would be very performance portable, but it never really materialized. It seemed that it was really kind of locked to just Nvidia GPUs, and the others just never really kind of materialized for us. And so we liked the fact that Kokkos has wide backend support for CPUs and GPUs from all the vendors. And then we had the backend support for some of our existing code for OpenACC and OpenMP to aid in our transition. We're also glad that it doesn't rely on compiler support, because that was one of our main gripes with OpenACC, is that things would take forever to get into the compiler. And then a very strong community of users. I mean, I've been on the Kokkos Slack and asked questions and answered questions numerous times, so thank you for everybody who were on the Slack and helped me out at times. So for this particular project, we were using the Fortran Language Compatibility Library, and this exists in the aid to transition Fortran code to C++ and Kokkos without the need to rewrite the entire thing. So that was a key aspect for us. We have a lot of infrastructure code that surrounds the one piece that we actually are starting with, and it simplifies the creation of the Kokkos data types from within Fortran and then passes them to C++ Kokkos. The execution code for that. And it allows us to call some aspects of Kokkos from within Fortran, so the Kokkos initialize and so forth. So while we were working with this, we found that there's quite a few caveats to using the FLCL, unfortunately. Some of these are actually not as big of a caveat anymore, because there's certain things that we were just mentioning in the question-answer session that the interoperability pieces of Fortran in 2018 are improving between Fortran and C, especially for arrays. But overall, the FLCL alleviates our need to write explicit Fortran interface code, especially for array data, but not all of it. It does not, some of the downsides to this, though, are that the interface code does not get generally checked by the compiler, because you don't have there's no such thing as a Fortran C compiler. You have C compiler, C++ compiler, or Fortran, but nothing between. So they can't really check each other's side of the interface to make sure you're doing it right. And so while we were doing this, we ran into a lot of data matching errors and things like that that really slowed our development. There's a lack of some full documentation on how to implement and use the FLCL. You pretty much have some few examples that come in the GitHub, but that's about it. So you really much have to come in with knowing Kokkos really well first, and then adding on FLCL later to your knowledge. And then the FLCL supports managed memory by default, and you have to do some extra work to get the dual views to get better performance. And then finally, near the conclusion of the project, like I was saying a second ago, we learned that some of the more recent Fortran C interface interoperability standards exist. So we'd like to definitely look into those in the future. So our project target overall was to really just kind of look at this one scheme amongst many. So we have this library of physics packages called the Common Community Physics Package, CCPP. And within it, there's multiple ones. And so in this case, we're using the YSU Planetary Boundary Layer scheme. So it's basically looking at the lowest 1 kilometer of the atmosphere, essentially, and predicting the turbulent motions that are within it, and then giving us bulk statistics back to inform the greater model around it. And so we started with this because it's fairly simple compared to some of the other schemes that were out there. So in this case, we only had 1,270 lines to look through versus like 7,000 lines for another library that does something similar. And then we also wanted to be able to start with one piece of the CCPP overall library, even though there is a lot of infrastructure code that goes around all of these physics packages that makes them portable and reusable in different models, not just a single one. And so we would like, at some point, if we get to that point, transition the actual infrastructure code as well, but for now we're just limited to the single package within. So our methodology overall for doing this is fairly straightforward. It's kind of similar to pretty much how you do a lot of GPU coding and porting. So we first identified our kernels. We identified our regions of code that were well suited for GPU execution, basically large loops that can be executed more efficiently in parallel. And then identifying converter variables. Each variable needed to be sent across the Fortran and C interface, obviously. And so we had to check each side of the interface and write that code manually to get that working. And then arrays, changing and getting those into the Kokkos views first, and then passed over the interface using the FLCL library routines. And then rebuild the Fortran loop body in C++ using the Kokkos parallel for structure. And then test the overall execution to ensure the new implementation was within our tolerances. And then just kind of recycle, repeat as for every kernel that we identified. And so the hardest part of this, obviously, was was basically number 2 and number 3, identify convert variables, and then getting those across the and re-implementing those in C++. Now, why do we re-implement in C++ and just the different kernels rather than the whole thing? Well, we wanted to keep our ability to retain the ability to work with our infrastructure code on the outside, and not just and additionally, we wanted the ability to retain the code to look similar to our internal scientists who are actually actively maintaining that code. And so they didn't want us to completely revamp the entire thing in one go. They wanted to see how things changed along the way. So our testing setup is our NOAA RDHPCS system called HERA. It's quite an older system now. It was based on the Haswells, Intel Haswells, and then some Nvidia P100s. Unfortunately, yeah, I see some groans. Yeah, sorry about that. We're getting new systems. We're finally getting new systems. But this is what we had on hand at the time. And so shortcomings, we're using Kokkos enables us to test performance probability. We could not get access to supported AMD or Intel GPUs. We tried to go to some of our cloud providers to try some there, but the ones that we got from Azure were AMD GPUs that were too old and weren't supported. And then when we tried it on the Intel Dev Cloud, we ran into issues with something within their cloud that wouldn't let us just set up what we needed. So we'll get around that soon. But for our performance, this is just kind of a first glance at our evaluation of our newly ported YSU scheme. Now it looks awful, I know. So the left one is the CPU Fortran, and these are, just orient you a little bit. The y-axis is the average runtime in milliseconds, not seconds, milliseconds. This is a very small piece of this code. And then the various columns are CPU Fortran, CPU Kokkos, and then GPU Kokkos. And so right now it looks awful because we're really falling on the fact that FLCL kind of limits us to UDM by default. So the managed memory of the Nvidia cards, and we didn't start off immediately and go directly to dual views because we were just kind of building this as we went. So what we want to do is go back and revisit, write this in dual views, and see if we can cut down, especially on the GPU Kokkos part, because that's really what's holding us down is the managed memory at this point, since it is such a small computational code. Additionally, if we were to do the whole infrastructure code like we intend to potentially, that would also reduce our data overhead because all of the stuff would be moved at the beginning, and all of these various physics packages would then be sharing and continuously reusing data that's already available on the GPUs. Okay, so some conclusions and recommendations. Some pros. Kokkos currently provides a good path to performance portability for us. It's providing a useful stepping stone to ease applications over to being performance portable. Without being able to without having to abandon Fortran completely, as we are largely a lab of Fortran developers, and does not require a compiler to be useful in its implementation as a library. We love that fact because the compiler-based ones seem to take a long time to get up to their own standards sometimes. And we like that the Kokkos team actively works to add back to the C++ standards because that kind of gives it longevity, and we want something that's going to stick around for a while and not just be a one-off. And then a very active and growing development community, as the people in this room all show for us. Some cons: the learning curve for modern C++ for Fortran programmers is rather high and time-consuming. That's not a Kokkos knack. That's a knack on all of us in the Fortran land, unfortunately. We're having a hard time making this transition. C++ still lacks standards for some of the basic things we Fortran programmers take for granted, so it's taking us a while to get used to the way to do it in C++, and then adding Kokkos on top of it is just making that a little bit more difficult for some of us. The Kokkos documentation for the FLCL could use some more improvement. And then if anyone's interested in using the interface, just understand that you have to be very meticulous about your checking and your compiling across that interface because it is not, it is very difficult, and very time consuming. And likely would be less of a burden in regards of time and effort to simply rewrite the whole Fortran code in C++, but again, for internal reasons, we didn't go that route just yet. All right, so our future work, these are some of the good things that really come out of this work is that we want to leverage our current Kokkos setup and gain access to systems with supported GPUs from additional vendors to test cross-vendor performance portability aspect. We only had the Nvidia P100s to test, and so we are actually looking forward to the fact that we have a new system coming online this year called URSA that will have an experimental partition with all three vendors, Intel, AMD, and Nvidia, at modern cards for us to try to continue and expand this work. Investigate improvements to the Fortran C interface standard regarding passing arrays to C++ and back to help us out. So we know that that exists, and so we need to really ramp up how to use that. And then consider re-implementing certain applications totally in C++, and then migrate away from managed memory to the dual view capability for hopefully cutting down on the performance overhead that we're hitting. And then finally, publishing results and recommendations for our other NOAA users that want to move on this pathway with us. So I'm currently writing what's called a NOAA technical memorandum to document the findings from this and hopefully provide a lot of best practices, helpful insight, tips and tools along the way. All right, just some acknowledgments. Again, thank you to everybody, the Kokkos devs and the Slack community for your help while we were working through learning all this. And then just acknowledge the NOAA software engineering for novel architectures under which we did this, the funding that we did this work with. And so any questions?
Thank you. So for the issue of checking the interfaces, right, the fact that there's no way to do that right now, is it worth trying to look into seeing if you can do that at the link stage? Like, is there a way of trying to see if you can get the linker to check the interface, like the call and callee? I don't know if it's worth looking at.
You know, I looked at a couple of different ways that maybe help this out. I didn't find any that really kind of helped us very well. It just kind of, it really came down to just being the most meticulous as possible about either side. The link stage doesn't really even help us too much either, because it's still just kind of on either side. It kind of builds out, and just throws it together. So it's really expecting the programmer to know what they're doing, unfortunately, yeah.
Do you know which way you're leaning between rewriting applications totally in C++ versus incremental porting?
So right now, we're staying with the incremental porting because a lot of our institutional knowledge is still so heavily Fortran that we kind of have to make more of a case at this stage before we start writing everything over in C++. We want to essentially get moving in that direction. We understand that there's certain limitations to Fortran that are holding us back, but we just have so much. Our momentum is still in the Fortran land right now, and we need to kind of shift if we're going to do that.
Yeah, just a comment that that's the route Los Alamos has taken as well. And our experience is that if you're going to go that route, that automation can really pay dividends in terms of writing those interfaces for you. So if you'd like to talk about it more.
Yes, I've heard from some people that there's some automation tools out there, and I really want to dive more into that. I just didn't have a chance to. But we could talk more, yeah.
If only we had a couple of really well-funded institutions which need, Fortran to Kokkos transition, and could actually put together a team to work on that problem, and support other people on that problem.
I can't speak for whatever LAP is doing, but EAP, we're good citizens, and I've already emailed Bruno the link to the publicly available stuff. So that's as best as we can do or gonna do, because ASC dollars means it's not publicly available code. So, or at least LANL ASC dollars make that extremely challenging.
Yeah,
Yes, we have time for one last question.
Yeah, hi, quick. Are you folks interested in making Fortran standard parallelism work with C++, including Kokkos? Is that a thing you want to pursue, or you want to just stop new stuff in Fortran and switch to C++?
I think it's that's a hard one, because we're kind of looking at both avenues and just trying to find what works from what doesn't right now for most of our use cases. I don't want to put words in anybody else's mouth, but because I'm not sure if, again, this is still kind of just more of an exploratory phase at this point. And so eventually we would like to see more into C++, but and using the tools that are available, because it seems to be that the more development is definitely on that side, and just kind of, it's not really happening as much as we'd hoped in Fortran land. But I'm not going to be able to make that decision, unfortunately, at my level.
Thank you again.